All right, we'd like to get started with our first afternoon session, Ice in Motion. We have Mark Fahnestock, Mikola King, James Lee, and the last person is Devin Dunmire, sorry. And I'm going to turn it right over to Mark to get started.
All right, well, thank you all for giving us your attention and coming to hopefully ask us some questions. It's a real opportunity for us to have actually give and take about what we're doing instead of the standard AGU stand up and talk for 12 minutes and get booted. So I'm talking today about a long record of change in Alaska that is strictly built from Landsat imagery, starting with Landsat 1. And the point of this talk is really that a combination of a very long time that the US has invested in this series of satellites and the large data capabilities of Google Earth Engine, where you have that data online, can create a really nice way to look at the Earth's changing ice cover. I'm specifically talking about Alaska and Yukon, but you could do similar things in other areas, maybe not quite as long a record. So what I have done is gone through all of the Landsat imagery pretty much by hand, picking out the best late summer, late melt season image when there's the least amount of snow for all of the ice in Alaska and the Yukon, and then I put it together in Earth Engine, and what you've just seen is a mosaic of August and September of 2019 built in Earth Engine. It's a virtual mosaic. It's just a list of scenes, but Earth Engine can raster that as something that would be 150,000 pixels wide. What we saw there in the end was a zoom by a factor of 256, so 8 steps in to look at the full resolution. Here you can see the 15 meter pixels in this pan-sharpened image. Again, that's just 2019. We've done that for every year from 1972 to present. So here we're looking at Columbia Glacier in 1972, and we're looking at 48 years of 20 kilometers of retreat of Columbia Glacier to 2019. So that's that 48 frame movie. It's going to now run through 4 times here, and you can see all sorts of things, which I'll point out if I can find the laser. So you'll see flow redirection over here. You can just see that these medial moraines get pulled out as the ice thins. You see a bathtub ring form as the ice in this region thins by well over 100 meters. You can see the retreat all the way back here to where this branch of the glacier has now divided into 5 separate smaller glaciers that were tributary to the original ice stream. And so this gives us this combination of being able to look at all this imagery at full resolution and then render it into movies where we would like to study. It gives us this opportunity to look at nearly a half century of change for ice in Alaska. So the next thing we're going to see, that was a retreating tidewater glacier. This is Hubbard Glacier, which this front advances over about 2.5 kilometers over this same period of time. Right there, there's a calving embayment in 2019. But this glacier is thickening and spreading in its valley rather than bathtub rings. It's pushing against everything on the side. And you get this sense of just this sort of inexorable advance of this glacier. And I'll point out, no calving embayments in this entire record, except for the last one in 2019, which is suggesting that perhaps in these really warm melt years, this glacier, which is pushing a pile of dirt along the floor of its fjord, and therefore it's staying stable because it's staying in contact with that moraine, these calving embayments, when they were seen by the USGS in the 1970s on Columbia Glacier, the US led the USGS to predict that the retreat of Columbia Glacier would begin in the early 80s. We don't know if this calving embayment forms year after year, whether Hubbard will then begin a retreat or whether this was an exceptional thing this year. It's one more thing that you can learn from when you have such a long record to set everything in context. This is a large Piedmont lobe. It's called Malaspina Glacier. We've changed scales here. This is more than 80 kilometers across. It's a big puddle of ice spreading out on the coastal plain. And over this period of 48 years, there are pulses in flow in these 2 glaciers on either side, and also the flow that's coming in is swinging back and forth. And as it does that, it carries these dirt bands, and it builds up this sawtooth pattern that when you just see it, it's really characteristic from satellite imagery. The very first Landsat images had it in it, but you don't get a sense of how it formed until you see 5 decades of it. So the second to last thing I want to talk about, you're looking down at the top of a peak here, and a bunch of slow-moving ice around all of this that flows down off of this peak. And in this last image here, most of these early images, they were quite bright. And that's because there was snow left from the last winter at high elevation on this mountain. And in this image from 2019, the only snow left from last winter is right there, just up against the side of the peak. And if we look at that one more time, you can see in the early images, there's quite a lot of snow cover, but in the later part of the later decades in this time series, and especially in 2018, 2019, there is no snow left. All of these glaciers, which all of which were retreating that entire time period, but in these images, none of them have anything left from the previous winter. They're effectively beheaded or they're starving. They just do not have any input to keep the ice there. So if that continues, they will just melt away in place. And then the final thing that I wanted to show you is this is another glacier that was a Piedmont lobe, and it's retreating. But the other thing that's happening here are a series of landslides. You see these debris bands in the later imagery, the first one of which appears in here in 1996 and is followed by several more. And each year they move downstream. I think with dimmer lights, we would actually see a series of ogives or ridges that look like annual rings in a tree. And these are being added to that record, the debris on the surface of the ice. But we can look down glacier for nearly 100 years and know that those landslides were not something that had been happening in basically the 1900s. But that's whether it's significant to recent changes in climate is sort of a point I don't have an answer to yet. And I think that's it for me. Yeah. We'll hand it over to Michaela. Yeah.
All right, hello, thank you. So I've used similar methods that Mark just described to study glaciers in Alaska, but applying them to glaciers in Greenland. So we're using optical imagery from Landsat 4 through 8 to monitor changes in front, so changes in retreat and advance, as well as changes in glacier speed. And we've done this for a 34-year record starting in 1985 through 2018. And so on the next slide, I'm going to show an animation, and I first want you to just to focus on the animation on the right, and that's going to show a retreating glacier. It's called Jensen Glacier. It's in northwest Greenland. And so just focus your attention on there first. And so the yellow line demarcates the front of the glacier in 1985, and you'll see through time that glacier has rapidly retreated. Now the teal line that you see kind of on the bottom of the figure, that is delineating what we call a flow line. And so we can extract velocities from a flow line and see how the glacier has accelerated through time in response to this retreat. And so looking then instead on to the left, you can see these are showing velocity. So as you move up on the y-axis, this is a greater velocity. So starting in the 1985, shown in the yellows, moving through 2018, we see that in response to this retreat, this glacier has dramatically accelerated. So this is just one glacier. We can look at changes in the front of glaciers for all major outlet glaciers in Greenland. So in this study, this is including over 200 glaciers. And so one thing that we've noticed is that retreat has been a pattern that we've seen across the ice sheet. So it's not just limited to one particular region. And so in these figures, the 4 figures are just showing the different major basins of the ice sheet. As you move down on the y-axis, that is indicating net retreat. So the further down you go, that's more net retreat through time. And on average, these glaciers have retreated about 5 kilometers. If you can see the areas that I've shaded in gray, that is marking the period of most rapid retreat. And what we find is that while all the glaciers have retreated in time, the period from 2000 to 2005 seems to be the most common time period where we see the most rapid retreat occurring. So we don't just track changes in retreat through time, but we're also really interested in being able to quantify the total volume of ice that these glaciers produce. And we call that ice discharge. So you can think of that as the flux of volume that these icebergs calve into the ocean. And so we can combine our observations of velocity with changes in thinning through time to get a volume flux of these glaciers. And so the figure on the right, this is showing total ice discharge, so the total mass loss from calving glaciers from the ice sheet through time, beginning in 1985 through 2018. And one thing you notice is it's almost like a stepwise increase in discharge. So beginning in the 1980s, it was near a little around like 440, 450, and it's increased by about 50 gigatons per year after 2000. And this is important because ice discharge is only one component of the total mass balance of the ice sheet. We also have to consider surface mass balance, or the accumulation from snow. And so in the 1980s, discharge, ice loss through discharge, was approximately equal to the total snow that was accumulated on the ice sheet. But starting in 2000, once we increased discharge, now your ice sheet is out of balance and you're contributing to net mass loss from the ice sheet. All right, and I'm going to play this animation here that's showing, as we move through time, we can see where these hot spots of mass loss are. So areas of red are showing net mass loss through time, beginning in 1985. And then the areas of blue are showing glaciers that have gained mass since the beginning of the time period. And so in general, most of the ice sheet, the margins of the ice sheet, have lost mass, but you will spot a few glaciers that have gained mass since the start of the time series. And then finally, bringing it all together, we're able to combine our time series of retreat, which I showed originally, with this ice discharge, and we see this very clear correlation where more retreat instigates greater discharge. So as these glaciers retreat, there's less contact with the fjord walls. That allows then the glacier to flow faster and calve more ice into the ocean. And so this figure on the right is showing in the 80s in the yellow, moving through close to present in the purple, we see that greater cumulative retreat. So as we move to the right, more negative indicates more retreat. We also get more discharge or more ice calving from these outlet glaciers. All right, thank you.
Thanks very much, Michaela. This talk follows on really nicely from what Mark and Michaela have been talking about. So where they've been discussing what's happening at the edge of the glaciers and the ice sheets as well. What I'm going to be talking about in here is what's happening on top of the ice sheet. So specifically about these meltwater lakes that are forming on top of the Greenland Ice Sheet. So this video shows the extreme summer melt season of 2019. There's lots of stuff in the news this year about how the Arctic was on fire, and there was an extreme melt season in Greenland, and we can see some lakes forming and then disappearing, and then also the snow line advancing further and further up. So for just an idea of the sense of scale, the width of this image is around about the width of California. So it's a really huge area that's actually experienced this melting. So just for a bit of context about what these meltwater lakes are and why they're important. So they represent a store of meltwater on the surface of the ice sheet, but they also have potential to drain catastrophically. So within a matter of hours, you can have huge volumes of water that drain straight down to the bed of the ice sheet and actually influence how the ice is actually moving and how fast it's flowing. So for what we did in this study, we used the same tool that Mark used for creating his videos, but we looked at MODIS Terra imagery. So for the first time ever, we've been able to harness the amount of computing power that's provided by Google Earth Engine to analyze the entire satellite record of MODIS. So that's every single day of every single melt season for the last 20 years. Altogether, it's around about 18,000 images that we've analyzed to create these maps of where lakes exist. And what we've found out overall, so this is an annual summary of each. So if we compare what's been going on in the early part of the millennium to what's been going on now, there's been an overall increasing trend in the amount of meltwater lakes that have been occurring in Greenland, and this totals to around about a 27% increase. However, you'll also see over the last 10 years, so you'll see 2010 and 2018 of particularly low years, but then 2012 and 2016 particularly higher. So it's also becoming a lot more variable, even though that variability is superimposed on a general increasing trend. You'll also notice that 2019 as well. So 2019, despite being an extreme melt year, and the second highest amount of runoff that's occurred from the Greenland ice sheets for the observational period, it's only actually the fifth highest number of lakes that have been observed in the Greenland for the past few years. So we have 2011, 2012, 2015, 2016, all had more lakes. And we're still trying to work out what precisely the reasons are for that as well. But what this generally means is that 2019, even though we had such an extreme melt year, and we're having these earlier large numbers of lakes, it means that the numbers of lakes that we're experiencing now could really pretty much be the new normal for Greenland that it's experiencing in terms of the frequency of the new lakes. So this begs the question as well, why are we having more lakes forming in the last 10 years? And to put it quite simply, more of the ice sheet is actually melting. But because more of the ice sheet is melting, we're also getting more lakes forming at higher elevations, and that's really important. So we're seeing lakes forming at elevations that what we weren't really expecting from some of the projections that were made. We weren't really expecting to see them forming at these elevations until 2050, 2060. So it's actually quite scary. So if you look at the graph on the right, we can see broken down by elevation is the elevations of unique lakes that are in the record. And as you can see that there's this nice distribution here for 2000 to 2009. But then if we compare it to the period 2010 to 2019, we can see that there's much more lakes forming at higher elevations. If we superimpose one on the other, so you can see there's significantly more lakes forming at these higher elevations. And also one of the reasons that we're getting more of these lakes is it's actually now looks like it's easier to form these form the lakes as well. So if we look at the graph on the right-hand side, in the blue dots, we can see, so on the x-axis we've got number of lakes. On the y-axis we've got the total amount of melts, the total amount of runoff happening on the ice sheet. So if we compare on the blue dots between 2000 and 2007, we can see that it groups quite nicely here, a nice positive relationship between the number of lakes and the overall runoff. And then we compare it for later on in the record, and we can see that there's been a shift to the right. So what that essentially means is that for a given amount of runoff, for a given amount of melt, it's you're getting more lakes. So you're forming more lakes for each bit of ice that you're melting. And this is likely to, due to some work that was published recently, presented this morning by Mike McFerrin on increased refreezing of melt within the subsurface of the ice sheet. So just to summarize, and then with a nice video of Peterman Glacier for the 2019 melt season. So the number of lakes that are in Greenland have increased by around about a quarter over the last 20 years. And these lakes are increasingly forming at higher elevations as well. Also, that these lakes are more now likely to form for a given amount of melt, and these are probably driven by refreezing of meltwater beneath the surface of the ice sheet. And then finishing off lastly, the extreme melt season of 2019 is potentially Greenland's new normal for the number of lakes that are forming on the ice sheet. And if you're watching this as well, you can see a nice lake drainage here quite late on in the season, so it just disappears in a flash. So I'll leave it there. Thanks very much.
All right, hello everybody. My name is Devin Dunmire, and I'm a PhD student at the University of Colorado. And for my presentation, I'm actually going to be switching sides of the globe and focusing on meltwater in Antarctica. Now, James just spoke to you about finding meltwater lakes at increasingly higher elevations, and in my presentation, you're going to see how we're finding lakes in Antarctica underneath the surface. Here is a video of a subsurface lake in East Antarctica. And as you can see in the video, you have a layer of ice below and then a layer of water followed by more ice above, kind of like an ice, water, ice Oreo cookie. Now, it's important to study meltwater because meltwater has been shown to lead to ice shelf instability and even potentially lead to the breakup of ice shelves, as was seen in the infamous Larsen B ice shelf breakup. We know a fair amount about the distribution of surface meltwater because surface meltwater lakes are easy to see in optical imagery. However, the distribution of subsurface water remains relatively unknown because they're buried beneath the surface, and so we need to use other tools in order to detect them. The next logical question that I always get asked is, how do these lakes form? The image that you see here is the result of a snow model. So we have a 1D profile of this lake with depth on the y-axis, and this image shows how this profile changes over the course of a year on the x-axis. And you can see that it starts out as a surface meltwater lake during the summer, and then as the weather gets colder, the top of this surface lake starts to freeze and it becomes buried by following snowfall. And this snowfall is able to insulate the meltwater underneath the surface, allowing it to stay liquid even during the winter months. So here is how I am detecting these lakes. On the left, you can see in the visible image, and you can tell from this image that you can't see any subsurface water, obviously. And then the right is a microwave image. So here we've been using microwave imagery in order to detect this subsurface water. And the reason we can use microwave imagery to see water that is even below the surface is because snow and ice are invisible at the microwave wavelength. It's kind of like if you heat up a cup of water and an ice cube in the microwave, the cup of water heats up much quicker than the ice cube because water is such a strong absorber of microwave radiation, and ice and snow don't strongly absorb microwave radiation. So here I'm going to highlight a few features in these images. First, we have dough lines. Now these are the result of a surface or subsurface lake that drained, causing a collapse of the surface, and these ring-like structures that you see on the image here. And next, we have the actual subsurface lakes, and you can see that they are completely invisible in the optical image on the left, but they show up as the dark spots in the image on the right, and that's because, once again, water is such a strong absorber of microwave radiation. So I mentioned before that we can even have this subsurface water lasting throughout the winter, and here are two places where I believe this to be occurring. This is a relatively newly observed phenomena, and so we're not entirely sure where this is occurring and what effect this winter water storage might have on ice shelf stability. On the left, we have the Wilkins ice shelf, and you can see at the bottom of the image these dark dots, which I believe to indicate the presence of buried meltwater in the winter. And then above them, you can see these ring-like structures that look similarly to the dough lines we saw in the previous image. On the right, we have George VI ice shelf, which shows a similar story. Finally, I'm going to show a time-lapse video of microwave images over George VI ice shelf. You can see in this time-lapse video that over the summer it gets really dark, and that's because this is when there's a lot of meltwater. There's a lot of melt occurring, and the top layer of the fern is more saturated with water. And then in the winter, you get these black dots or dark blue dots that dot the ice shelf, and those indicate the presence of buried meltwater in these locations. I'm going to zoom in on one area and play the video again, so just focus on that blue lake right there. And you can see that after the last melt season, the signal changed and the lake is now bright. And that indicates that the water has drained from this lake. And this is actually one of those dough line structures that we saw in the previous images. And actually, one of my advisors, Allison Banwell, just returned a week ago from Antarctica, where she visited this dough line and saw ice ridges along the rim and huge melt channels that lead to the center of the dough line, which is about 20 meters below the outside of the dough line. So to conclude, I am studying subsurface lakes in Antarctica, and these lakes are able to form and last throughout the winter due to sufficient snow insulation. I have used a combination of visible and microwave imagery in order to detect these lakes, and they appear to be prevalent on the Antarctic Peninsula. Thank you.
All right, thank you to our panel, and we'd like to open the floor to questions from reporters, please. Any questions from our reporters in the audience?
My name is Ned Roselle. I write for the Alaska Science Forum. Mark, I have a question for you on the Hubbard Glacier embayment there, that chunk out of the face of Hubbard. Two-part question. When did you notice that, and what might cause that?
So I noticed that calving embayment about 3 weeks ago when I put together the 2019 mosaic and remade the movies. My talk, the title of my talk was a 47-year record because the abstract went in before this melt season. That kind of embayment is, it was termed a calving embayment on Columbia Glacier, and it is because the ice there has broken off as icebergs, but the ice on the sides has not, because it's in contact with that submarine shoal. And it's almost always the case, or maybe it is always the case, that there is a subglacial channel that reaches the head of that embayment. And so there's some relationship between where there is a channel underneath a tidewater glacier and the formation of those embayments, the calving that leads to their formation. So it could be that the very strong melt year this summer led to greater subglacial discharge, and that may have accentuated the process that forms those bays. We're not sure.
Do we have more questions?
Hi, Jonathan Amos, BBC News. Michaela, I was interested in seeing your little dot bouncing along there. It doesn't seem to do anything dramatic in 2012 when there was the big melt then. Why was that, do you think?
So the 2012 was a big year for surface melt, but that doesn't necessarily mean that the actual volume of ice that you see calving as icebergs is going to increase. So there's a lot of research right now looking at how meltwater, oh, there goes my mic, how meltwater influences glaciers. And in some cases, it can actually cause short-term deceleration. So you do see in 2012, there's a sharp acceleration, but then a very sharp deceleration as well. So these are two different systems. You have your surface melt, and that melt will make its way through the outlet glaciers, but it doesn't necessarily cause an increase in the iceberg. So what we were looking at there was just the volume of ice calving, not the surface melt.
So the explanation for the jump that does occur, I mean, what do you put that down to? So, I mean, so you bump along at, I can't remember what it was now, at about
34 years.
Yeah, you bump along and then you start to accelerate upwards. So what happens at that point where you start to accelerate?
Right, so that acceleration occurred beginning around 2000, and that coincides with the widespread retreat that we saw. So a lot of glaciers in most regions of the ice sheet, their fronts had retreated further inland, and so that allowed the ice to flow faster. So that acceleration in ice was bringing more ice into the ocean, and that was directly due to the widespread retreat that started occurring in those years. And what triggered that retreat, it varies by what region of the ice sheet you're looking at. So southeast Greenland, a lot of that had to do with warm ocean waters that started melting the fronts of the glaciers, and that caused retreat. But across the ice sheet, the retreat was what caused the acceleration, yeah.
More questions from the audience? Anyone? Do we have any questions on the chat, Sarah? No questions on the chat. Last chance. Okay, let's thank our panelists and thank you all for coming.